one of the things I wanted to do while putting the keynotes together this year was to make them a little crunchier than they were last year. Get people who are not just interesting, but are technical, experts in their field, people who can stretch your brains wide open and thrust new thoughts and ideas in, whether it's pleasurable or not. I know my next speaker will be able to make this pleasurable because I was in his Haskell tutorial on Monday. So Simon Peyton-Jones is a researcher at Microsoft Research. He is one of the fathers of Haskell. He wrote the main Haskell compiler, GHC. GHC, yes. And we've asked him here today because he's been researching in his work on Haskell not just the language, but some of the parallelism possibilities that can be extended through there. So I'd like to welcome on stage, if you will, Simon Peyton-Jones. You do have to take the microphone with you, Simon, that's right. So Simon's going to be talking about transactional memory and concurrency, and in particular something called software transaction memory that he's been hacking on. Simon, thank you.
Hi. Yeah, the microphone got attached to my chair, and, but it appears to be back together. That's very good. So you'll be relieved to hear that I'm not here to sell you a product, or even to sell you a language, or to sell you Haskell. I'm really here to sell you an idea. So here's the context, which we've had largely set up for us by Intel. So now we have to program multi-cores. Parallel programming is something that we have to do rather than being optional now if we just want more performance. And oversimplifying wildly, I'm going to say that you can broadly think of two ways of building parallel programs. You can use task parallelism, in which you spawn off multiple threads, each with their own program counter, and then you have to arrange for those threads to communicate and synchronize with each other. Or else you can do data parallelism, which means doing the same thing, that's a single program counter, to lots of bits of data at the same time. So in this talk, I'm just going to concentrate on task parallelism. If you want to hear about data parallelism, come to my talk this afternoon, in which I am going to be focusing much more about Haskell, whereas this talk isn't Haskell specific at all. So here's the context for task parallelism. The strange thing is that the state of the art in making threads communicate and synchronize with each other is fundamentally 30 years old. There's been very little progress in the last 30 years, even though we've been thinking for a long time that it's a hard problem, and it's a problem we don't know how to solve, and it's a problem the current solution is not satisfactory. So our current solution is locks and condition variables. They're sometimes called synchronized methods or monitors, but fundamentally it's locks and condition variables. And they're fundamentally flawed, I think. And the reason I think they're flawed is because they don't compose well. That is, you can't build big programs by gluing together small programs that already work, by gluing them together in an unchanged way. But just in the last few years, an idea has come along which is called transactional memory, which I did not invent, so I'm happy to be able to say that it's, for me, been like a ray of sunshine, right? A new way of thinking about writing parallel programs. And that's the idea that I want to get across to you today. So first, just a very quick review of what's wrong with locks. Right? So what's wrong with using locks? After all, we've been doing it for a long time. Lots of programs use locks, and some of them even work most of the time. So what's wrong with locks? You can forget to take a lock, and that gives you a race when two threads are modifying the same data at the same time. You can take too many locks, or you can take locks in the wrong order, and that leads to deadlock, in which the program does nothing at all. You can forget to signal a condition variable, and then threads waiting on the condition variable don't wake up. And if you want to do error recovery in a lock-based program, it's particularly difficult because you've gone around taking some locks and now something bad has happened and the program has done something unexpected and you've got to arrange to untake the locks, restoring the state of the world to an internally consistent state so that the rest of the threads don't get confused. This is really hard to do right, and it's hard to test because it doesn't happen very much. But it's not, even this lot is not the worst thing. The worst thing is that locks are absurdly hard to get right. See, here's what I mean by absurdly hard. Here's a double-ended queue. And I want it to be scalable, so I want to just put one lock per node rather than one lock for the whole queue. And so while the queue is long, one thread can be putting data in one end of the queue, while the other thread is taking data out from the other end. But if the queue gets short, it gets to be difficult to make sure you do the locking right? If the queue contains 2 or 1 or 0 elements, it's hard to get this right. And here's what I mean by absurdly hard. If you write the code for just a sequential program, it's an undergraduate project to get queue insertion and deletion going. If you want to do this scalable lock per node thing, it's a publishable result. I kid you not. There are international academic conferences with a succession of papers that have been published about this very problem. That's what I mean by absurd. So the thing about atomic blocks, which I'm about to describe very briefly, is that they return that problem to the undergraduate level. It becomes easy again. And here's the idea. So this is the one idea I want you to remember. All we're going to do is we're going to take some sequential code, and we're just going to wrap, or the code that would work in a sequential program, and we'll just wrap atomic around it. What does atomic mean? It's just an idea taken from the database people. As Maurice Herlihy is fond of saying, if you want to get a good idea, look at what the database people were doing 20 years ago. Because they probably thought about it. So this is the same idea. So we're just going to do a transaction against memory rather than against the database. Right? So to a first approximation, you write the sequential code and wrap atomic around it. What does that mean? That means that the code inside the curly braces is going to run with an all-or-nothing semantics. Right? So that gives the atomicity. And it's going to run isolated. So while that code is running, it's not going to see modifications to the state of global variables that are affected by other threads. Okay? So it's the A and the I in the ACID for database transactions. So one thing you want to notice about this already is it can't deadlock because there are no locks, right? I didn't take any locks. It's almost as if there's one big lock. You can imagine one big lock being taken, run the code, release the big lock. That wouldn't be a good implementation, but it's one way to think about it. So you can't get deadlock, but there's only one lock to take, so you can't take them in the wrong order. Another thing is it makes error recovery very easy. If you get an exception thrown in the middle of this atomic block, then the whole atomic block is undone. That is, it is as if it had never executed. Remember, it either all executes or none of it executes. If an exception happens, it's easy to make it so that none of it executes. And that means that the state of the global state is unchanged from the way it began. So you don't have to do any restoration of invariance. So how might you make this work? So again, steal the idea from the database people. There are lots of ways to make this work. Here is just one of them, which I'll give you because I like a visceral feel for how these things can happen. So we'll use optimistic concurrency. So the way you execute this is you take no locks at all. You just execute the code against possibly changing contents of the memory that other threads might be altering at the same time. But every time you do a read from memory, you log it in a thread local transaction log. Every time you do a write, you don't write into global memory, you write into the transaction log. So when you do a read, you need to read the transaction log to make sure that you're not reading something that you've written, because then you'd want to see that value. Then finally, at the end, you've got saved up a log of all the reads and writes that have happened, and now you need to do something that is truly atomic, but the programmer never sees this. The system has to arrange to atomically read from memory all the reads that you made and check that they're the same values, and then, if they are, write the writes back into memory, all in one atomic step. And how that is done doesn't matter. Very clever people have spent years figuring out how to do that, and we're going to pay them to do it just once so that the rest of us can benefit from it. If that fails, because some of the things that you read have changed, well then, that's fine. The commit fails, and you just rerun the transaction. Remember, nothing has happened in global memory yet. So that's how it works. So much for just atomicity and keeping threads separate. But when you write a concurrent program, you often have producer-consumer stuff, where one thread is producing something, another thread is consuming it, so the consumer needs to block if there isn't enough data. How are you going to do that with atomic threads? This is what you would use a condition variable for normally. So here's how you do it. I've written some code here that's meant to be indicative of the kind of thing you might want. If the queue you're getting something out of is empty, then call retry. So retry is the new primitive, and it means the following. It means abandon the current transaction and re-execute it. Well, if you re-execute it right away, the buffer's likely to be still empty again. It would be correct, because you then retry again, but the processor would get very hot and not make much progress. So what you want to do is you would like the system to block the thread until what? Until one of the things that it read on the way to that retry has changed. So a transactional memory system is going to look at the transaction log, see which locations you read, and then block your thread until one of those locations has been changed by another thread. So it's a very nice, simple, modular blocking condition. And there's no condition variables in here, right? There's no lost wake-ups, because the system is dealing with the wake-up. And furthermore, it composes nicely. So here is two queues, right? So I'm going to get an item out of one queue, and I'm going to put it into a second queue. And let's say that if you take an item out and the queue is empty, you want to block. If you put an item into a queue and the queue is full, you want to block. So now this little atomic transaction must block if either the first queue is empty or the second queue is full. And it's really painful and non-compositional to have to take those conditions out and put them at the front. You don't want to have to think about how put item and get item works. So with a transactional memory system, you just say, you just write this code, and if either of these retry, the whole transaction will retry, and it'll be rerun when the conditions become true again. So it's very compositional. That is, you can build without changing put item and get item. You can glue them together into a bigger transaction. That's the point I want to make to you. The third idea that I want to get over to you is choice. So we've got atomicity, blocking, and choice. So what does choice mean? Choice is what it would be select in Unix, right? Or wait for multiple handles in Windows. It's when you want to say, I want to wait for one thing to happen or another thing to happen. So here's an example. You want to take an item out of a queue, and then you want to put it into one of two queues, depending on which one is not full. So the semantics of this choose or else construct says, try to run the bit that's in the queue.putItem, q2.putItem, try to run that. But if it calls retry, the very same retry we've just been discussing, if putItem calls retry, do the or else part. It's a bit like a handler, right? Then if you try to put it into Q3, and if it retries, the whole choose or else construct retries. And then you're going to block waiting for, well, what? Well, here's what you're waiting for. So now there are three things we might need to wait for in this transaction. Three places where retry might be called. It might be called in get item, if the first queue's empty. It might be called in put item for Q2 or put item for Q3. So you want to wait until either, if this transaction blocks because there's not room in Q2 or Q3, you want to wait until either of those things has been changed. And that's, again, what a transactional memory system will do for you. So again, this is compositional, right? I didn't need to change put item or get item at all in order to use them in this context of a choose or else block. And the choose or else block itself is nested within a transaction. So you might wonder, this seems all very nice, but how much does it cost? After all, we care about how fast our programs run. So the first thing to say is, yes, there is a cost, right? There's all this transaction log stuff or some other implementation of the abstraction. And so a lot of compiler technology can reduce it quite a lot, really quite a lot. And the other rather more trite observation is programs that don't work are pretty useless. So I'd rather have a program that worked a little bit slower but actually gave the right answer than one that would work really fast and gave the wrong answer. And the other thing is to say is that because you get this much finer grained concurrency, your program may scale much better when you use transactional memory than when you use locks. Because in order to make the lock-based program work right, you have to use very coarse-grained locking. And transactional memory, in effect, gives you very fine-grained locking. So here, very briefly, are some sort of indicative figures that were measured by my colleague Tim Harris. So the toolbar in the, let's see, the second and third bar from the left are using coarse-grained locking and fine-grained locking, respectively. The vertical axis is execution time. So fine-grained locking takes longer because you're doing more locking and unlocking operations, but it's scalable when you add more processors, so that's why you might want to do it. The bars on the right indicate the cost of transactional memory. Still more than purely sequential code, but actually less than even fine-grained locking once the compiler technology has been applied. And here's how it scales as you add processors. So here the vertical axis is time, the horizontal axis is number of threads or number of processors involved. And you can see that the transactional memory lines are pretty flat, which means that the cost per operation doesn't go up as you add processors, whereas coarse-grained locking is hopeless, right? It just goes right off the top. So here's the one slide I would like you to remember, if you remember nothing else from this whole talk. This idea of atomic blocks, transactional memory, with atomic, retry, and or else, and don't let anybody kid you that you just need atomic, right? You've got to have something like retry or else to deal with blocking and choice, right? So with atomic, retry, and or else is a real step forward. I feel as if it's like writing in a high-level programming language instead of writing in assembly code. I completely concur with my colleague from Intel about not wanting to use the assembly code of locks. But just a word of caution is that writing in high-level languages is great, but it's still possible to write buggy programs in C++ or Java or C#, sadly, right? It's still possible to write buggy programs in high-level languages, and the same is true of transactional memory. You can still have concurrency bugs in your program, I'm sorry to say, but they will be more interesting bugs. They will be the bugs that you want to spend your time working on. Right? So there's lots of fun to be had here. This is a very hot research area. Lots of papers coming out, and I think you're going to see lots of product announcement and development. I don't speak for Microsoft or Intel or anybody else, but I'd be very surprised if you don't see transactional memory on your radar sometime very soon. But I cannot resist taking the opportunity in this large forum to point you at STM Haskell, which has had transactional memory for over a year now, and which is free software, and which you can download later today from haskell.org GHC. So Haskell is a functional programming language, but it has concurrency primitives built in as well. And in particular, it's had transactional memory for quite a while. Indeed, that's where the retry and or else ideas were born for the first time. So thank you very much. Maybe I'll see you later this afternoon.
Bloody good. So did we succeed in Crunchy then? I think we did.